Okay, this is the fourth video for Chapter 8, Substitution Reactions. We've been talking about SN1 reactions now and how they differ from SN2. So let's talk about the stereochemistry of the reaction. Remember, for an SN2 reaction, if you have a chiral carbon, you get complete inversion of stereochemistry. The configuration inverts about that optically active carbon. What happens in SN1 reactions? Well, recall that SN1 reactions go through a planar carbocation intermediate. So if you're planar, when the nucleophile comes in, the nucleophile can attack from the bottom or top of the carbocation in the second step. So what happens are we get two configurations from that. We get, if we have a chiral carbon, both the R and the S. Regardless if you start with a chiral carbon, what the chirality of the carbon is you start with, you end up racemizing or forming a racemic mixture, 50-50 mixture of enantiomers in your final product. Alright, so let's go ahead and let's look at, let me erase this comment right here because I don't like it. I don't know why I put backside attack here. This SN2 reactions, the nucleophile approaches from a backside attack, but we're looking at SN1 reactions. And for an SN1 reaction, the nucleophile attacks a planar carbocation intermediate. So let's look at this example here. Here's an example of a reaction where our alkyl halide, or Rx, has a chiral carbon. Okay, so we're starting with the chiral carbon there. It's an R configuration at the chiral carbon center. It's optically active. We only have one stereoisomer. Now, what type of alkyl halide do we have here? Well, this carbon, which is chiral, is attached to 1, 2, 3 other carbons. So it's a tertiary alkyl halide. Tertiary alkyl halides do not do SN2 reactions. They only do SN1s. So this has to be an SN1 reaction. Our nucleophile here is a weak nucleophile. It's protonated. So remember, the substituting group will be the OCH3, and when bromide leaves, the proton will be associated with it. So that will be our byproduct. Alright, now in this reaction, what happens is we start out with the R configuration, but we get both the inversion of stereochemistry and the retention of stereochemistry in a racemic mixture. We form both pairs of the R and S enantiomer of a methoxy substituted product. So SN1 reactions give us racemization, 50-50 racemic mixture. Why is this? Let's look at the mechanism. So I'm going to bring this up here. Alright, here's the mechanism of the reaction again, just like a regular SN1, just like the one we saw before. The first step for an SN1 mechanism is the dissociation of the halide to form a carbocation. So as the halide leaves, we end up forming a carbocation intermediate. So what's attached to this? We've got a benzene ring, so we've got a phenyl group. We've got an ethyl in the back, and we've got a methyl in the front. Alright. So once we form the carbocation, remember the carbocation is planar now, so that p orbital there extends top and bottom about the plane of the molecule. So if the nucleophile, the methanol, attacks from the top, we end up adding methanol to that side. And what happens is the ethyl group bends down, go back to tetrahedral, and the methyl group puckers down with it. When we deprotonate, we're going to deprotonate there with the bromide. In the final step, we end up adding OCH3, the methoxy group, and we form one enantiomer. Okay, so that's the one product formed. Now, which product is that? Is that R or S? Can you remember how to do it? The oxygen's higher, and then the benzene's attached to the most carbons, and then we've got the ethyl, and so the lowest is in front, so we reverse it. So what is this? This is the R enantiomer, right? Okay, this is R. Now let's come over. What if instead of the methoxy group or methanol attacking from the top, the methanol attacked from the bottom? The groups would bend upward to form the tetrahedral at this point, with the ethyl in the back, the methyl still in the front, but now we have the substituted and protonated version of the substituted group. When we deprotonate, we end up getting OCH3, so HBr is our byproduct, ethyl's in the back, and methyl's in the front. So this is the enantiomer. This gives us the S enantiomer of the compound, and we see that because of the planar transition state, right here, the one I'm erasing, because we're planar, it's a carbocation intermediate, we can get a nucleophilic attack from the top and bottom. So we get both. So bromide was on the top initially. If we attack from the top, we get retention of that configuration. And if we go in the nucleophile on the bottom, which is the back side, we end up getting also inversion. So we get both inversion and retention of configuration. So if you start with a chiral carbon and make a chiral carbon, you'll always get a racemic mixture for an SN1 because it goes through the planar intermediate. Alright, so let's do an example of an SN1 reaction. An SN1 reaction where we see the racemization of a chiral carbon. So here we look at our starting material. We've got Rx here. And Rx, there's a chiral carbon. It's technically not chiral. So let me go back and let's change this. Let's put a methyl group also here. Let's put a methyl group up. Alright, now I'm happy. Now that's a chiral carbon. So the carbon here is chiral. The iodine is up. Now remember, the iodine's going to leave, and we're going to form a carbocation intermediate. So when the product reforms, when we add our nucleophile, which is our water here, and look, water is also a polar protic solvent. So it's the solvent and the nucleophile. Now, water is HOH, right? It's a neutral nucleophile, so what gets substituted once the hydrogen's deprotonated in the end will be OH. So we're going to substitute the iodine for the OH group of the nucleophile overall after it's protonated. So our product here then, because we start with a chiral carbon at the iodide, we're going to get both inversion of configuration with the substitution. So here's my methyl groups. They didn't react, so they don't change. But we're also going to get retention of the configuration. The iodine was up, and the hydroxy substitutes from that planar transitions or intermediate. We also get retention of that configuration of that carbon. So we end up making two products, where the OH is back and where the OH, the nucleophile, once it's substituted, is also up. 50-50 mixture, a racemic mixture of the two. Let's look at the mechanism of this reaction to just prove it. So what I've done is I'm going to put it in a chair form. So I'm going to redraw this. And the reason I want to do it in chair is because, hey, it's cyclohexane and we haven't done a chair for a while and it'll be on the final, so why not review it? So we knew the iodine was up, so I've got the iodine up. And at the 3 and 4 positions, the methyls are also up. One of them's axial, one's equatorial. If you don't know how I'm drawing this, before the final, you need to go back and review, actually even before the next exam, review how to draw chairs and substitute them. So this represents our starting material with the iodine up. And let's see here. At the 3 and 4 position, the methyl group's up as well. I'm getting messy. But see how those are up, up, up? This is up, up, up in our chair. So I've drawn the correct structure. Alright, now, what happens first in an SN1 mechanism? The rate determining step, dissociation of the halide. So the first step, the slow step, RDS, will be to form a carbocation intermediate. So as that leaves, the hydrogen planarizes. It's not axial or equatorial anymore. It's right in between. And we still have the methyl up and the methyl up. This is the carbocation intermediate that's formed. Now at this point, the nucleophile can react. The water was the solvent, it's polar and product, but it's also the nucleophile. Many times in SN1 reactions, the solvent is the nucleophile because it's the protonated version of a negative nucleophile. It's a polar product solvent. So whenever the water adds, it can either add, here's your p orbital, from the bottom or the top. So we end up getting two products formed. If we attack from the top, that's axial. And I'm going to go ahead and deprotonate too, so minus H+. Well, I'll keep it protonated for now, why not? So here's the one substitution product, the hydrogen goes down, and this is when we attack from the top. And then we can also have water attack from the bottom. If water attacks from the bottom, we end up getting it added equatorial, and the hydrogen goes to axial. Alright, so we see how these are different. Here when the water is added, and all that's left is deprotonation. When the water is added here, it's in the axial up position. When the water is added here, it's in the equatorial down position. If you go back, that's exactly what we showed here. The axial up is the retention of configuration, and the equatorial down, when it reacts from the bottom and then deprotonates, is from the bottom position, and it ends up equatorial or down. But remember, these can ring flip as well, so axial becomes equatorial and so forth. Alright, so I just thought it was fun to put a chair in there to kind of remind you that we do need to remember this stuff for the final. Alright, because an SN1 reaction goes through a carbocation intermediate, we have to remember one of the fates of a carbocation is possible rearrangement. Possible rearrangement. So when you have an SN1 reaction, which involves a carbocation, you always have to look out. When that carbocation is formed, is there a more substituted carbon next door to the carbocation that could possibly give you an alkyl or a hydrogen shift to form a more stable carbocation? Here's an example below. Consider this reaction. Here we have an alkyl halide, there's the bromine there, and we're reacting it with methanol. Now, this is a 1, 2, 3, 4 carbon chain. It's a 2-bromo, 3-methylbutane. Alright, so the bromine is on the second carbon. We expect when we react with methanol, using methanol, it's polar and protic, so it's a weak nucleophile and also a solvent. We expect the OCH3 of the nucleophile to substitute the bromine directly at the second carbon. So we expect this product here, A. And we see that we get some A, okay? But then we also see that here's the second carbon. In this product, we get the methoxy added to the third carbon. How did that happen? It happened due to rearrangement of the carbocation intermediate as it formed. And more interesting is that the major product in these two reactions, the one that's not been rearranged, A, and the one that's being rearranged, B, the major product is the rearranged product. So the fact that there's two products and these are not like stereoisomers of one another tells me there's actually two reactions going on. Now, what type of alkyl halide do we have to start with? Well, if we look at the halide, the carbon it's bonded to is bonded to 1, 2 alkyl groups. So the type of halide this is, it's a secondary alkyl halide. Now remember what we said about secondary alkyl halides. They can do both SN1 and SN2 reactions. Because they're a little bit bulky for backside attack in SN2, but they're also stabilized, but they're not too bulky. If they form a carbocation, they're also stabilized through hyperconjugation, so they're somewhat stable as well. So how do we know which reaction is going to predominate? Well, we look at other factors. Because the secondary alkyl halide can do both SN1 and SN2, we look at the nucleophile and the solvent. Here we have a polar protic solvent. Polar protic solvents, notice the hydrogen on the oxygen, that's a proton, it's slightly acidic, favor SN1 reactions. And then the nucleophile is not a negative charged nucleophile, it's not a good nucleophile, it's a poor nucleophile. Another reason we would favor an SN1. So the SN1 product is favored here, and it is the product that goes through the carbocation intermediate and we get the carbocation rearrangement. And this is our major product. So let's look at the mechanism. Alright, so to form B, we see there's a rearrangement. It has to be through carbocation or an SN1 mechanism. The first step of an SN1 is dissociation of the halide. So we end up forming the carbocation intermediate. So let's see, there's 1, 2, 3, 4 carbons in the backbone. 1, 2, 3, 4. And the bromide left the second. There's a methyl here. So we end up forming a secondary carbocation. Right? I'm just going to go to skeletal figures. It's easier. Now, once the carbocation is formed and bromide is dissociated, it's going away. All right? Now the nucleophile is supposed to come in. But remember, nucleophile-electrophile reactions that between two molecules are slower than rearrangements. And there's also a hydrogen here. We see that the carbon next door to the carbocation is branched. See how it's just not a straight chain? It's branched. So look for hydrogens or alkyl groups, hydrogens migrate faster, that can migrate to form a more stabilized cation. If that hydrogen migrates over here, we end up getting that carbocation rearrangement through that 1,2 hydrogen shift. So now the hydrogen comes over here. Now there's already one hydrogen on there, but when the hydrogen shifts, now the carbocation's here. Okay? Now the nucleophile, the methanol, can come in and react. And it's protonated still. And then we can deprotonate with the bromide or more methanol. Either one will work. And we end up getting the rearranged methoxy product. So instead of at the second carbon, we see substitution at the third through a carbocation rearrangement. There's a lot of explanation of this in your book, and I really hope that you're looking in your books as you study. The lecture is a good source to go over things after you've reviewed them by studying in your book. The higher you get in chemistry and biology, the more you'll realize there's so much material that it's almost impossible to cover during a normal, regular lecture. And the more and more you realize that the book is the primary source of your studying, and you come for clarification. So hopefully this is clarifying things you're reading in your book for you. Alright. So, for a summary of our SN1 reactions, how do we know if we have an alkyl halide, a nucleophile, a solvent? How do we know what reaction is going to take place? Remember, for SN1, substrates that are tertiary and secondary are favored because they will form stable carbocation intermediates. Now they can be secondary or tertiary allylic or benzylic or regular as well, but primary and methyl do not favor SN1s because they do not form stable carbocations. Alright, the second thing is the nucleophile. Remember, if the nucleophile has a full negative charge, it's a good nucleophile. That's an SN2. We want poor nucleophiles. We want protonated, or we say protic nucleophiles, such as alcohols, water, carboxylic acids. Now, if we use a carboxylic acid as a nucleophile, the nucleophilic atom is this one. So that would do the substitution of the halogen, and you would end up forming, once you lost the hydrogen, this is the R from your R group, an R oxygen bond, so you'd form an ester functional group. There's a lot of those examples in the text. Alright, so we want poor nucleophiles though, things that have the hydrogen on them, they're neutral, not negative. And the third thing we want is polar protic solvents. Alcohols, water, carboxylic acids, these are all good examples of polar protic solvents. The interesting thing is they are also good examples of weak nucleophiles. So for SN1 reactions, usually the nucleophile is also the solvent in the reaction. Okay, so let's look at some examples of comparing reactions and all of the different parameters, the characteristics, the alkyl halide, the nucleophile, the solvent, the leaving group, in order to determine whether or not we should go the SN2 or the SN1 route. Now, if you are SN2, methyl and primary alkyl halides are always favored. If you're SN1, tertiary alkyl halides are favored. But secondary alkyl halides can do SN1 and SN2. So if you have a secondary, look for the other parameters to determine what will happen. So let's look at the first reaction here. Okay, in this first reaction, we see that we have a secondary alkyl halide. There's 1, 2 carbons attached to the electrophilic carbon. And we notice there's chirality at that carbon center. So we need to think about if it's SN1 or SN2, whether it's inversion of configuration, like SN2, or you get a racemic mixture out, like SN1. Alright, so our nucleophile here is cyanide. Remember cyanide, there's a full negative charge on the carbon. This is a good nucleophile. Good nucleophiles, very nucleophilic, favor SN2. And also notice our solvent is polar aprotic, it's acetone, also an SN2 type of solvent. So this reaction here will be an SN2 reaction. The cyanide will form a nitrile. It will replace by a backside attack in one step, and we'll get a full inversion of configuration. So for SN2s, we only get one product for this reaction. The CN, the nitrile, and then the methyls are up. Nothing happened at those centers. There's no carbocation intermediate, and we get full, complete inversion of configuration about the chirocarbon that's reactive. Alright, let's look at the next one. Same starting material, okay? Now, this time we have a different nucleophile. Notice it's not negative, it's neutral. This is a poor nucleophile that favors an SN1 type of mechanism. And then notice our solvent is also our nucleophile. That's indicative of a polar protic solvent. It's very indicative of an SN1 type reaction. So we've got polar protic, that's SN1, and a weak nucleophile, SN1. So remember that SN1 gives retention of racemic mixture, racemization of stereochemistry about a chirocarbon reacting. So we're going to get two products here. We're going to get the inversion of configuration when OCH3 adds. And that'll be 50% of our product. But we're also going to get the retention of configuration. When OCH3 substitutes, not adds, but substitutes the iodine in this SN1 reaction. And do you remember why we get a racemic mixture? Because SN1 reactions go through a carbocation planar intermediate. Alright, so we've talked about SN1 and SN2, and we know what types of nucleophiles and solvents everything favors. We're going to expand the topic and look at intramolecular reactions. These are reactions that instead of involving two molecules, the nucleophile and the alkyl halide, it's one molecule that contains both the nucleophile and the alkyl halide attached to itself, and the molecule reacts with itself. So we have these intramolecular reactions. So here's an example. Here we have a compound that on one end we have the alkyl halide. We've got a bromide attached to a carbon chain. And on the other end we've got an oxide, which we know anions are nucleophiles. So we've got the alkyl halide here, and we've got the nucleophile here. We know that nucleophiles react with alkyl halides. Now how's it going to react? What type of alkyl halide is this? Well, the carbon here attached to the bromine is attached to one other carbon, so it's a primary alkyl halide. The nucleophile is completely negative, so we have a good nucleophile. So this will be what type of reaction? It'll be an SN2 reaction. The nucleophile will do a backside attack and attack the electrophilic carbon and push out the bromine, so the oxygen will make a bond with the carbon at the other end of the chain. So what ends up happening is we form a cyclic compound when it reacts with itself. See? One end of the chain is the Rx, the other end is the nucleophile, and when they react, nucleophile backside, SN2, kick out the bromine, you get the cyclic ether. Alright, so if you want to know exactly how this happens, and can it actually happen, let's bend the bonds and rotate them, because we know single bonds rotate, to see that we form a pseudo six-membered ring here of the starting material if we bend it. And we can indeed give the oxygen a backside attack to bromide, and in one step, as we're forming the bond and breaking the bond, this is the transition state for the SN2 reaction, we end up forming the cyclic ether. Alright? Now, can any size ring be formed? It turns out that due to steric strain, we don't want rings that are too small, and due to entropic effects, entropy or disorder, we can't get rings that are too big. So 5- and 6-membered rings are always favored, and they form the fastest. If you have a longer chain or a shorter chain, and those rings can't form quickly, the molecules will start polymerizing or reacting molecule to molecule rather than intramolecularly. Alright, so 5- and 6-membered rings are best. Let's look at some examples, though, of 3-membered rings that actually can form. How can you form a 3-membered ring? I thought it's too strained. Well, it still can exist, remember. And when you have the proper formation of your nucleophile and alkyl halide, meaning they're next door to each other, you can form a special 3-membered ring called the epoxide. So consider, this oxygen is a nucleophile attached to a 6-membered ring, and directly next door we have the alkyl halide. Now notice that both of them are wedged up, so it's up, up. If we look at the chair conformation of this structure, one will be axial and the other is equatorial. Now the alkyl halide here is secondary. It's bonded to 2 carbons, so it can do SN1 or SN2. Because we have a strong nucleophile that's negative, it would have to be an SN2 reaction. Now, how do the nucleophiles react with alkyl halides? The nucleophiles come in from the back side. The back side of the alkyl bromide is over here. Can this oxygen bend and come in from over here when it's bonded directly next door? The answer is no. The only way that the oxygen can react with the alkyl halide when it's tethered on the ring together like this is by going straight down. So no reaction can occur here because we're set up with a good nucleophile and a polar aprotic solvent for an SN2 reaction, but because we cannot get the backside attack, no reaction will occur. The molecule will remain open as is. Now, look at the one below. The reaction below, instead of a dash and a wedge, dashes, we have a dash and a wedge. If you look in the chair conformation, the bromine is axial down, and we've got an axial up for the oxygen. Now the oxygen, if it comes over to overlap to form an epoxide, it's directly lined backside of the bromine to do the epoxidation reaction. So this reaction will occur and we form an epoxide. So when you have a 1,2 trans substitution, these are trans, they can be diaxial and you can end up getting a backside attack of your alkyl halide. So from the starting material, we can, from the top, get the epoxide reacting and kicking the bromide out. Okay? So the reactions that occur intramolecularly, you need a nucleophile and an alkyl halide both tethered together on a ring. You can get a ring closing reaction. When they're tethered together in a long chain, usually the 5 and 6 membered rings are formed most stable. But if you have substitution outside of a ring of an oxide and an alkyl halide, like an iodide or bromide, those are your best leaving groups. They react the fastest, so those are always our favorite. When they are substituted trans to one another, they can react diaxial, which is exactly what's needed for the oxide to do a backside attack to favor an SN2. If you can't do an SN2 because you're cis, the only possible way to get a substitution is by SN1 reaction. Alright? So look in your book at that. That's an interesting topic, and you'll probably see something like that again in the future as we move on in other chapters, these intramolecular reactions. But this will conclude Chapter 8, Substitution Reactions of Alkyl Halides, including the special topic here at the end.